Hello everybody and welcome to Live Science, but today we're not quite live. This is a recorded episode still coming to you from the Creation Museum and Creation Education Lab. I've got Professor Faulkner with me again today. As you can see behind us, we just finished recording our episode on force and using the marble track. But there were some questions that came in from our Physics of Flight episode the other day that I wanted to address. And since I've got the physicist with me, I thought that'd be a great opportunity to do that. So briefly the other day, we talked about the basic principle of lift and how if we're just using the simple concept of lift, a wing that has equal length sides doesn't create a differential pressure lift, but one that had the cambered side does. We talked about the Wright brothers and how they did that. Now, there were some simple explanations in that video. It's way more complicated than that. We can make this wing fly, and a lot of modern planes do in fact have this wing shape by changing the angle, and we call it angle of attack, and then that creates a center of pressure, and there are all kinds of different things we can talk about there. But a couple of the questions that came in as we were talking about forces of flight and lift and drag and those different things, some different things about airflow were discussed with aerodynamics. So the question came in from David. He said, if we don't have gravity, would the ball or the frisbee, we talked about discs and frisbees, stay in motion?
Oh boy, it gets tricky.
It does.
Because a lot is left unsaid.
Yes.
If you didn't have gravity on the Earth, then we wouldn't have an atmosphere.
Yep.
And so then this whole thing about Bernoulli's principle and pressure differences won't apply because there's no air there. Mm-hmm. Perhaps what he was talking about was maybe in a quote-unquote weightless environment, maybe aboard a large space station.
Sure.
There's no place really big enough to do this in the ISS, but suppose we built a bigger one.
Let's build a bigger one.
Yeah, and in which case what you would have there is effectively you're in free fall, so there's no effect of gravity per se, but you would have atmosphere. And suppose the thing is moving along. Well, if that were the case, you would have those forces being produced. Like, for instance, this wing, if it's got air flowing past it like this, there's going to be lift pushing up this way. But unlike an airplane where there's weight pulling it down, this thing's just going to keep rising up and up and up because there is no weight counterbalancing. You don't need much. Think about it. If you're weightless, you don't need to spend a lot of effort staying where you are because you're not going to fall anyway.
An astronaut inside the space station can flick his finger off the wall and propel him across the room.
And he can just go spread eagle in the air and just not do anything.
Okay, so if he were to throw a ball inside of there, if there were no spin on the ball, let's keep it simple there, and the ball were just moving,
right,
it would just continue in a line.
Right.
There's a little bit of drag. It would probably slow down a little bit.
I want to get a little technical here. Okay. If the ball is going fast enough, you will end up with slight irregularities, and it'll cause the ball to kind of spin randomly.
Sure.
And when that happens, it'll cause the ball to kind of dance around. We call that in baseball, it's called a knuckleball.
Sure.
There are some pitchers that can throw that. It's like 60 miles an hour, and it floats all over the place because there's no spin on it. But most of us can't throw it that fast, so it's not going to be an issue. But I want to make that one clarification.
Yeah, certainly. What if I stepped outside of the space station in my spacesuit and I were to take this ball and throw it toward Mars?
Well, in this case, it's going to be very different from what you had inside the air. Inside the air, you started to mention drag a little bit, and the ball is going to slow down very gradually and come to a stop in the air environment in the space station. But once you go outside in the spacesuit and you throw the ball, it's going to keep going and going and going. It'll never stop.
Until some other gravitational pull grabs it.
Or someone catches it or something.
Yeah, so maybe we'll become a satellite of Mars and start orbiting Mars.
Yeah. And by the way, if there was spin on the ball, that would, inside the space station, it will cause the ball to, if it's spinning like this, it can cause the ball to deviate left or right. If it's got a top spin, it'll cause it to dip,
down.
and more so than it would on the Earth, perhaps. Well, gravity plays a role there. You may rise if you have a backspin, which would be hard to do on the Earth, but you could make it happen in the space station. But if you're outside the space station, in a spacesuit, and you throw this ball with curve, it's not going to deviate at all. It's going to keep moving.
There is
the same direction.
Yeah, there are some crazy YouTube guys who do that off of a giant dam, and they drop a basketball with backspin on it, and they watch the Magnus effect and how it will sail forward and give that momentum forward. Pretty cool. You can go watch those videos with your parents. I'm not.
Don't try
I'm
this
not
on.
endorsing any. Their scientific knowledge is not top drawer, but
Let me ask you, did they do this with permission of the people who own the dam, or did they just do it?
I think so, yes, because they've done lots of them.
Okay.
Very
all right.
interesting things.
Don't try this at home.
Yes.
or at
yeah.
a dam.
All right, so the follow-up question then from David was, do you have to have aerodynamics in space since there's no air? So we talked about how, like I showed 3 different discs. One had a very blunt edge, it's a short-range putter. Next one is a mid-range, and then the distance driver has a very slim profile to fight through the air. Yeah. So would any of those things be beneficial in space?
Not at all. If you look at the ISS, it's got all these solar panels and everything. It looks very spindly, and it looks very non-aerodynamic because there's no real air to interact with. Now there is a little bit, and its orbit's slowly decaying. It's falling to a lower and lower orbit. They'll have to boost it up again at some point, but it's very slow. It takes years for this to happen.
Yeah.
Now, if you look at these space capsules that they launched with, and the space shuttle was flying, it had some aerodynamics because it had to pass through the air to get up into space.
Yeah, we've got to go through the atmosphere to get back.
But a good counterexample of that is the Lunar Excursion Module that they used in the Apollo program 50 years ago. It was like a little spider or something with 4 legs. Not aerodynamic at all.
It didn't need to be.
Because it was inside of a shroud until they got into space, then they opened it up and they then connected with it.
Yeah.
But they didn't have to go through the air like the command module did. It was shaped like a cone.
Yeah, so today they would launch those things on like a Soyuz rocket and very aerodynamic to get out of the atmosphere. But once we leave the atmosphere, there isn't the effective air.
That's it.
So you mentioned boosters to maintain orbit, and that kind of takes us to another question. So Titus asked as a follow-up question to that, how does the fuel burn with less oxygen at higher altitudes or no oxygen in space?
Okay, in the case of space, you got to take your oxygen with you.
Yeah.
Most of the, not all, but most of the rockets we've used, particularly for people, they mixed hydrogen and oxygen together. The external fuel tank on the
like the space shuttle.
No, it had both oxygen and hydrogen in there. The Saturn V, the Apollo program had all of that, and they mix those together and they get it to ignite. But
so you've got to have oxygen still,
oh,
because combustion requires oxygen.
If you have
so
fuel
you
in space, if you just have fuel, it ain't going to burn.
And using solid fuels is much more efficient
because
than
the solid
taking
fuel
gas.
has the oxygen inside the fuel with it.
Yes.
The solid fuel boosters on the side of the space shuttle were like that.
Yeah.
The disadvantage of those is once you turn them on, you can't turn them off.
Yes, they use up all the fuel in them at once.
The advantage of a liquid fuel like hydrogen is to shut it off. All you have to do is shut the valves off, and that stops the burn. Now, as far as height is concerned, altitude in the Earth's atmosphere, as you get higher, the proportion of oxygen remains the same, but the amount of oxygen decreases.
Because that's the partial pressure law, we call that in chemistry.
You go to Pikes Peak, 14,100 feet. The air pressure is only 60% of what it is at sea level.
Yeah.
So you've got 60% of nitrogen, 60% of oxygen, everything else. I had a pastor of a church I went to over 35 years ago, almost 40 years ago now. And he went on a mission trip for a while with some relatives who did missionary work, I believe, in Ecuador. And they were inside of a building, they had a fireplace, and they were going to build a fire. They brought some wood in, brought some kindling, and then to get it started, they brought in a gasoline can. He was getting ready to run out of the building. He goes, "What?" Because you never use gasoline inside to start a fire. In fact, it's not very smart outside. You want to use diesel, kerosene, or something.
Yeah, something that burns more slowly, doesn't create the vapors that will ignite in a fireball.
Yeah. But they were up in the Andes Mountains.
Yeah.
And it turns out the gasoline doesn't have a big conflagration. It burns, but about the way kerosene would.
Sure.
And so it was pretty safe. Again, don't try this at home, kids.
Yeah.
Please don't try this at home.
Back in the old days when you were a kid and carburetors were on vehicles, even if you drove up a mountain, you might have to get out and adjust your carburetor to allow more airflow to get enough oxygen to keep the fuel burning.
And one of the neat things about modern automobiles is they don't have that problem. They have fuel injection.
Yes, we have electronic circuits that control all those things.
And all fuel and air mixture. You know, on cold mornings, I don't miss carburetors at all.
Not at all. All right, so one more follow-up question to what you just said. If I'm in space and I've got a satellite and it's got rocket boosters on it to help adjust that orbit, if I take the fuel with me, I take the oxygen with me, if there's no air in space, what's creating the thrust?
Oh.
One of the forces that we talked about in flight.
Right. It's a matter of action-reaction. You can try this yourself if you have some roller blades. Get on them, take a ball, a baseball, a softball, anything heavy you can, and throw it. And as you do, you will recoil backwards a little bit.
Yes.
If you've ever done any rifle shooting or shotgun shooting?
I'm an instructor.
Right.
So I do that a lot.
But I'm talking about the kids at home.
Sure.
They shouldn't do this without their parents' supervision.
Absolutely.
But a shotgun is a very good illustration of this. You always want to bury that stock into your shoulder, because if you don't, it will leave a nice bruise, I've been told. So I always pull it in because it does have recoil. Get on your roller blades and fire the shotgun and see how much you
feel that reaction.
You'll roll backwards. Same thing's going on in space. You got a rocket sitting here. The ignition happens, you burn the fuel, and the burnt fuel gets spewed out the back at a very high speed. And as it does, you're pushing on that burnt fuel, but by Newton's third law of motion, action-reaction, it pushes back. And it pushes the rocket forward. What confuses people many times is they think that, like a jet airplane, it's doing the same thing, except it's not taking its own oxygen, it's already pulling it out of the air. And they think it's pushing against the air, and indeed there is a little bit of that going on. But think about this, the front of the plane has to encounter air, so that what you gain by pushing off air here, you'll more than lose by pushing against the air in front of you. So even in the atmosphere, a jet works, or even a rocket works by action-reaction, just as it does in space. You don't need a medium there.
All right, thanks for those answers.
My pleasure.
Okay, another question that we got on the physics of flight had come in from Aiden, and Aiden asked, why does a frisbee turn when you throw it? So if you've used something like this catch frisbee out in your backyard or in the park, you throw a frisbee, and if you throw it really hard, it tends to turn over to the right if you're a right-handed thrower. Now, when we think about rotating objects in motion and the wing and all of these different forces that are coming in, things get really complicated really fast. So I'm going to try and explain all of these things in a relatively detailed manner without getting too carried away. So the answer I gave initially in our program the other day had to do with one of the forces, and we'll talk about three different forces, called differential drag. So if the disc is spinning like this in a clockwise rotation, if you're a right-handed thrower, and any of these principles we just reverse if you're a left-handed thrower, or if you throw it on a forehand throw, they're rotating in a clockwise manner. So that means this edge of the disc is rotating toward the air if I'm throwing it this way, and it's creating a lot of drag on this side, and this side is rotating away from the air that it's encountering as it's moving forward, and so there's less drag on this side. So if you throw it slowly, what you'll notice is there's more drag on this side and there's less drag on this side. So it's going to slow down this side's rotation, and it will tend to turn to the left if you throw it. Okay, so that's because of differential drag. That's one force that's acting on the frisbee when you throw it. A second force is called gyroscopic precession. Okay, now that's a giant word. So if you think about gyroscopes, maybe you've played with a little metal gyroscope and you pull the string and it spins a disc inside of it really fast, and you can get it to balance and walk on a string, all kinds of neat things. But when things are in motion in a circle, they tend to have a very stabilizing effect, because as the motion is going, all of the energy around the outside of the disc where there's more weight is being transferred in all kinds of different directions, and it starts to balance it out. Now, if you look at the surface of the catch frisbees that you've got, we've got little dimples in the top of this one, and my dog has grabbed it a few times, so there's some teeth mark and imperfections. So all of those things are going to add to drag and produce different airflow as the surfaces are rotating. So there are literally hundreds of things you'd have to take into account as you're thinking about throwing something imperfect like this disc. So if we think about a very strong throw or a very fast moving throw, if this were moving through the air, it would basically overcome the force of the differential drag on the sides by stabilizing it with the gyroscopic motion. So when it's going really fast, it would overcome that differential drag. When it's going slow, it's going to cause it to turn to the left. And in disc golf, they've actually developed a system of numbers that helps us describe all of those different properties. So this disc has a 9-4 -2 2 ratio. So this rating tells me how fast I need to throw it. So out of a 1 to 14 range. This tells me how glidey it is, how much it tends to stay in the air. This third number, the -2, tells me how likely it is to move to the right during its flight. And this 2 at the end tells me how much it turns to the left at the end of the flight when it slows down. So they have these little guides to help us understand that. So when I think about this disc moving through the air, I'm going to try to balance this on this little pin here. If this disc is spinning in the air as it's flying through, okay, wind is encountering it on this edge and causing drag, and there's less drag over here because this side is moving away. And as it spins, you can see it stabilizes itself. I can rotate this pin down here on the bottom and it stays relatively flat. Okay? If I were to try to do that with this disc with all these chew holes and marks and irregularities in it, I would get a lot more wobble. So the flatter and smoother the disc is, the cleaner its rotation is going to be. Okay, now here's the part about, I got to get this spinning quickly, so here's the part about gyroscopic precession. You would think if this is flying through the air, there's a little bit of air pressure down right here on the nose of the disc. Okay? If I put pressure down right here, what do you think is going to happen to the tilt of the disc? Is it going to tilt down towards you, or is it going to go in a different direction? So you can make a prediction right now. We'll get this thing spinning again. If I can keep it flat. Get it spinning as quickly as I can. There we go. If I put pressure down on the front, like air pushing on it, notice it tipped to the left. Okay, it's wobbling over to the left side and tilts down to the left. That's because of what we call angular crisis. What we call angular momentum. So the momentum as the disc is spinning is being transferred, not right here at the point, but it's turning around and the energy is being transferred over to the side. So if I push the spinning disc, apply a force here, it's actually going to tip this way. If I were to push a force on the back side, if it's spinning in this direction, it's going to translate that energy around and tip this way. So gyroscopic precession helps us explain that as well. So if we can get this thing flat again, if I push down on the back side of the disc, it should tip down over here. And you can see the plate tips down at this angle if I put force over here. So understanding all of those properties and how all those things work together helps me understand the flight of my disc, and professional disc golfers will use those characteristics to shape the way they fly. The third force, so we have the differential drag, we have the gyroscopic precession. The third force is what we call center of pressure. And as the air is moving over this disc and it's rotating, that's going to cause airflow to move in little bubbles around the surface of here. And we call that turbulence. So as the air is coming across, it's not perfectly smooth, but every time I hit a tree or this crashes into the ground or a rock, it gets a little ding in it. And that's going to make little wiggles in the airflow. And so predicting exactly where the pressure center is on all the disc, as remember, as a wing, this is creating lift with a high pressure zone on the bottom and a low pressure zone on the top. But if that pressure zone is centered off to the side, it's going to cause the disc to turn this way. If it's on the front, it's going to cause the disc to turn downward. So all of those different factors. So why does a frisbee turn left or right when you throw it? It's a very complicated answer, but I hope that just helps you understand how amazing it is as we try to understand all that God's created, the complex details that He's worked into all of His pieces. All right, we hope you will continue to enjoy these programs through the weekend. We've got some special things planned for you this Easter weekend. We hope your family will be able to gather around those things and be encouraged by them. Even if your local church family isn't able to meet, or if you're doing those virtual services and those types of things, these will be a supplement to you and encouragement to you. So God bless, and we'll see you next week.